Good morning, I'm Ting from Child Mind Institute. Today I'm going to talk about a microscale area organization of the macaque cortex in vivo. So for a century, the delineation of the functional brain units is a fundamental challenge in neuroscience, and the pioneering efforts have used a combination of histological, cytoarchitecture, and mining architecture examinations, along with lesion study, to differentiate brain area. And non-human primates brain model in this effort provides a promising vehicle for advancing translation neuroscience. Recently, algorithm, which is based on the functional connectivity gradients, has been demonstrated the ability to characterize the human brain organization on the group level and individual level as well, and has been showed has good retest reliability if the sufficient data are required. And this method was first proposed by Alexander Cohen in 2008, and then Gagenwicks modified this method to bring it to the folded cortical surface. And how does this work, gradient-based postulation works? This is an example. If we look at the functional connectivity of the supramarginal gyrus, we find even the angular gyrus it is pretty close to the supramarginal gyrus on the surface. But actually, the functional connectivity pattern would be so different. Actually, it's totally opposite. So we would assume that supramarginal gyrus and angular gyrus would be belong to a different functional area, and there could be a functional boundary among them. So if we look at the functional connectivity across the cortex, if we cross the boundary, then we could find dramatically change of functional connectivity. So we can measure those change by the gradients to see if any potential functional boundary there. So for each vertex on the cortex, we can measure the similarity of functional connectivity and calculate the spatial gradient of the similarity. And then we can shape the gradients to get the binarized edge map. At the final stage, we can just average the binarized edge map across 10,000 vertices and gets the edge density map, which represents the possibility of each vertex could be identified as edge on the cortex. And we can start from this edge density map, which we can call functional boundary map, to get the postulation. And the previous study suggested the postulation from this boundary map actually corresponds to the task activation. We would like to validate this by monkey data and see if any corresponds to the histological structure. But before we go that far, there's a few questions we need to be addressed. So the first one is feasibility of the boundary mapping postulation in individual macaque. And second is we need to validate the postulation in terms of the functional data itself. And third one is the reproducibility and the stability of the postulation algorithm. In order to answer those questions, we collected 4 adult recent macaque, and 2 of them come from the Nice and Klein Institute. We collected the monkey while they are awake, watching movie, and we also collected the data while they are under anesthesia. And another 2 monkeys were from the Oregon Health and Science University. They all collected under anesthesia. In terms we need to enhance the quality of the monkey data to increase the signal-noise ratio. So we also test if we also look at the contrast agent effects, and part of the data were collected while they have injected the contrast with Mayan, and another part of the data were without Mayan. So let's look at how the functional boundaries looks like. So this is an example from NKI monkey, and which has 140 minutes data. We split the data into half and half and just look at how those two halves of the data set could be like reproducible, could have the reproducible functional boundaries. The first two were the gradient map and the edge density map. As you can see here, the spatial correlation of the gradient map is 0.92 and 0.71 for the edge density map. It's pretty good. And also we could look at the dice coefficient for the pacillation. It's reached 2.76. So now we know it's the functional boundary map is reproducible, and how does it correspond to the traditional histological boundaries. So we compare those puzzles to the Brodmann area, especially area 17, which is a primary visual context. We could get a pretty good correspondence to those Brodmann area. Next, we look at the pacillation homogeneity in different states. So the green and the red line here is the data we collected while awake and anesthesia, but both with Mayan. And the dark blue and light blue here is the data we collected without Mayan, just a pure bold. And we see like the data with Mayan is always get good pacillation homogeneity than the data without Mayan. Then the next question is, okay, we know the data with Mayan is better than without, but how about we don't know even though it is good compared to the non-model. So we split the data into half and half, use half the data as a reference and another half as a test data set to test if it is homogeneous. So the red dot here is from the real data. And for the non-model, we just rotated the real data, real pacillation on the cortical surface, and we randomized 1,000 times to build up this random model. And the black dot here is average homogeneity across those puzzles. And you can see here the red dot is very significant, better than the non-model, which suggests the functional gradient-based functional pacillation works. So we know it is reproducible, it is homogeneous, and the next question is how many data should we have to get a stable, accurate estimation of the functional connectivity, gradients, and edge density. So we split the data, use the half of that reference, and for the test data sets, we randomly selected a certain amount of the data, start from 8 minutes, 20 minutes, 40 to 80, to look at how similar or the test data set could be from the reference data set. So here we suggest like 30 to 40 minutes data could reach the plateau for the functional connectivity, gradient, and edge density, but we need more data for the gradient, for get a pacillation rather than just a stable functional connectivity. But again, we see like here, the blue line here is the data without Mayan. No matter how much data we collected, the data without Mayan never reached a similar similarity with the data with Mayan. So we highly suggest if you're going to look at the data for the monkey, it's better to use the data with Mayan. So next, we also want to explore the inter variation in different states, different monkey, and different MRI center. So the bottom right is a similarity matrix in different subset, different state, different monkey, and different, it's really like all the information there. So I summarize it on the top left. So the red frame box highlights the within monkey similarity. It is pretty high than the cross monkey within states, which highlighted by the blue color. And this suggests that the functional boundary could have the potential ability to use as a fingerprint to identify the individual monkey. Another one, we can look at the dark purple here, which highlights the monkey cross sides, which is the similarity is pretty low. This could be related to the differences between the two sides. We use different coil. One is surface coil, another one is knee coil. And one interesting thing we find is we collected one monkey just using pure rest, not watching any movie. So we find the similarity between rest and movie is pretty much similar with each other. But when we look at the data for the awake versus anesthesia, it goes down. You can see the gold color, gold dot here. So let's look at how those functional connectivity on the different states looks like. So we can see here the top left two were the functional connectivity on the while they are awake, pure rest, and they're watching movie. And they're kind of pretty much similar, except that the visual network have more connected to each other on the movie paradigm. This could be a suggestion like maybe for the monkey study, movie paradigm is more preferable because the monkey could tolerate more while they are scanning. And for the anesthesia data, we can see across monkey, they looks more similar than the awake data. So the differences between awake and anesthesia is pretty much more driven by the awake data. So to summarize, I would like to insist on 4 points. First, gradient-based area boundaries are highly reproducible in individual macaque with sufficient data. By sufficient data, I suggest 30 to 40 minutes with contrast. Second, the gradient-based oscillations show internal validity. And third one, rest and naturalistic viewing during awake imaging show similar functional property. Last, the individual area organization is unique, while the awake and anesthesia and anesthetized states show distinct profile. I'd like to thank for all the colleagues and the collaborators from OHSU, and you can find more information on the poster and also online. Thank you.
This talk is open for questions. All right, I think that we'll move on to the next speaker. Thank you again.